It's a very good time to enter this field for the young scientists. Of course, that's very crowded, but that's a unique opportunity. Not everybody has the chance of participating in a revolution like this.
Now is the time for a new generation that makes use of this tool to do something that we didn't think about before. And this is, I would say, the era that we're in right now. These are the big challenges, and this is where the young generation has to come in and provide answers. There may be surprises how well these things work, and some of these early ideas might then be realized in a way that really will change the world.
Like John Bell was saying, shut up and calculate from Monday to Saturday, but Sunday, just think.
In this episode of the 632 Nanometer podcast, join the team in Princeton to witness the reunion of two trailblazers in quantum computing. Peter Zoller, a professor at the University of Innsbruck, and Ignacio Cirac, a professor at the Max Planck Institute of Quantum Optics. When Peter Shor theoretically proved in 1994 that quantum computers could perform at least one classically intractable computation, most physicists were skeptical that a hardware implementation of a quantum computer could be built at all. By 1995, Zoller and Cirac had described a revolutionary physical model for a quantum computer using trapped ions and laser beams. The methods they pioneered eventually led to the commercial quantum machines built by startups like IonQ and Q-Era. Together, they've co-authored over 70 papers, merging theory with experimental breakthroughs.
Since both of your names on the paper, how did it happen? How did you meet each other? So there's the part that when we actually met. This was still in Innsbruck. That should deeply explain this whole timeline. I was working at the University of Innsbruck back home in Austria. And I got an offer to move as a professor to the University of Colorado in Chile. Chile was my main association there. And before that, Ignacio had sent me an email. It was just a few months before, and he appeared out of nothing. And it was one of these situations, you can explain this in more detail, that as a PhD student in Spain, you had the opportunity or obligation to go abroad. And for some reason, maybe you want to explain that now, you somehow decided to work with me. But I was already had somehow packed my bags to move to Colorado. And this was the starting point. Maybe you explain this, Ignacio.
I was a PhD student in Spain, and at that time, with the fellowship that I had, you had the opportunity to spend 3 months abroad, and then you could choose a place, and so you just have to write to the scientists and go there. But looking around, and what I was interested in was what Peter was working at that moment, so I wrote him, and he accepted. And then I arrived, this was 1990, September 1990, to Innsbruck, and when I arrived, Peter told me, I have to leave. So basically, that was, but we had some overlap at that time, and then that was how we started, and we worked a little bit together, and then I finished my PhD and wanted to go with Peter as a postdoc to Boulder because he was already in Boulder.
Yeah, I was in Boulder for 4 years until 1994, where these quantum computing things were happening, and of course Ignacio was there during all of this time, and we were working together on problems like Dave Wineland was actually down the road building optical clocks. They learned how to do trapping of single ions, of many ions, with the application of the atomic clocks. And then they learned how to laser cool these particles to the ground state, to the motional ground state. Was this kind of achievement towards metrology, the ultimate metrology. During this time, we got to know these systems because Dave Wineland, and we very often had to, for example, referees his papers internally. So was, under quotes, forced to learn this kind of physics. And then with Ignacio, together, we started to work on some of these theoretical problems. And coming back to the question, how did trapped ion quantum computing actually happen? We were working on the problem. We had the string of ions, like what Dave Wineland had in the lab with the laser cooling and the laser manipulations. And we were coming up with models like James Cummings type models for many particles that was like cavity quantum electrodynamics, but not with, but with phonons. And we had all of these ingredients, but it was more a playground, and we could do all of these things. We knew we could make squeezed states of phonons, but who would actually care about them? So it was at that moment that we had a sort of like an answer, but what was the question? And then was this conference in the summer of 1994, ICAP in Boulder, organized by Carl Wyman, Dave Wineland, and also Steve Smith, I think. And this is when Arthur Eckert appeared, and both of us were sitting at the talk. And maybe Ignacio want to tell the story.
Yes. So as Peter was explaining, so at that time we were working on ions, and the trend there was to cool the ions for atomic clocks because then they can build with them very good atomic clocks. And so we took a little bit a different approach. So we wanted to look at quantum physics with trap ions. So that was our goal. So we started thinking how to observe quantum physics phenomena and things like that. And at the same time, then ICAP took place in Boulder, where we were both of us, and then they invited Arthur Eckert to give a talk. So maybe to put a little bit of background, at that time, Peter Shor in that year had already not published, but sent to friends his paper about factorization of
which is now 30 years ago, exactly 30 years ago, right now.
And then it circulated and people got very excited. So this is why they invited Arthur Eckert to try to translate it for physicists and to see what was the point of these factorization algorithms, quantum computer. And so then Arthur Eckert was at ICAP giving one of the plenary talks, explaining what a quantum computer is to people who never work on anything like that. And then we both were sitting there. And so he was explaining that if you could build a quantum computer, that would be fantastic. If you could do factorization and many other things that are to be discovered. However, at that time, it was not known how to build a quantum computer, or even if a quantum computer could be built in principle. And so we were sitting in the audience, and for us, I think it was a challenge. So right after the talk,
Eureka moment. We said, let's say, wow, we got the answer. Now it's a question.
Since we started already into quantum computing, so where does the quantum computing come from? So I was trying to dig in literature, the roots of it. So I got into Feynman's lecture there was like one in 1982, 1985, simulating physics with computers. And then there was the follow-up on top of that. But I think there was like even some works before that. So it seems like back in 80s or 90s, and since you lived at that time, so what was the situation? What were like the views, and how did people see the development of the field?
So maybe you can explain a little bit the history of that, because it's actually very interesting. So in the late 70s, so people in physics started doing computations for lattice gate theory, so to study high energy physics with computers, but the computers were not powerful enough. At the same time, some people were thinking that if you start making chips smaller and smaller and smaller, because at that time we had the first chips, then at some point we'll reach the limit in which you have to put a chip or in a bit in an atom, and then you will have to be confronted with quantum physics, and then you will not be able to do computation anymore. So quantum physics was, let's say, a problem for computation. And then some other people were thinking that maybe that's, on the other hand, an opportunity, because then you have quantum physics and it can be exploited. And that's what there was, I think, some very remark in some paper by some Russian scientists. But the one who really developed was Richard Feynman in a conference. He went to a conference which was about computation. And then he was saying that actually if we want to solve these problems in physics, like in lattice gate theories, that classical computers will never work. However, we should then think about how to solve quantum problems with quantum computers, with quantum physics. He developed the concept of a quantum computer as we have it now, basically. So he was not only a visionary, but he also set up the principles of quantum computation, and then he developed them later in 1985. But I think that one can really trace back, so when quantum computation was born, and one can very safely say that it was Richard Feynman.
I think one should add here that, for example, David Deutsch, who was, of course, related to Arthur Eckert, he played a very important role in all of that. And I remember that when Arthur Eckert gave this talk, he explained to us, if you would like to build a quantum computer, and he addressed this question then to the AMO community, to the atomic physics community. What you need is qubits, what are the properties, how to manipulate. This is the first time I heard the word gate, that we should no longer call this thing a spin 1/2, but now it's a qubit, and how to entangle and so on, what the basic questions are. And so the challenge was very clear that you need a quantum memory of qubits, and atoms, of course, for us was a very good candidate, in the case of the ions, because they had been developed for the atomic clocks. And so all of this experimental work for atomic clocks was immediately available then also to build a quantum computer. And of course, so all of these things somehow came together, that we had to build a gate-based quantum computer. And then the question was how to do gates. And I would say the central aspect of this whole proposal that we made at that point was really not that there was just a whole machine of trapped ions. You had the possibility of cooling, of readout, this notion of quantum jumps that occurred before, and this was converted into a readout of the qubit. Then in addition to all of these things, then to do the corresponding gates. And this entanglement gate was, I would say, maybe the center of it, but it's also, I think, very important that it was some broader picture of this. Was the proposal that we made was one for a complete quantum computer from the very beginning to the very end, and not talking about one particular element of this thing. And we came out of these talks knowing, well, we got probably the right framework for doing that.
But prior to this talk, so your interest in trapped ions was to build better atomic atomic clocks, or what was the motivation there for you to study these systems initially?
We started thinking about how to cool ions because they are required to stop them in order to build good clocks. But then we soon realized that in the same tools in which they can cool these ions, they can observe quantum mechanical properties, which people didn't think about them in the context of trap ions. So people at that time were looking at some other systems like atoms in cavities. And then we saw that the same physics and the same phenomena that people predicted for these other systems could be observed with trap ions. And this is why we were very excited to observe. So
Not only observed, but actually being done in a better way.
Yes.
That's right. So you would like to reach the strong coupling regime in cavity QED, but you always get this damping, and so it means smaller and smaller cavities. But here, by just cranking up laser power, one could actually get cavity QED models that were closer to the dream of what one wanted to achieve.
Yeah, but I think that maybe the big difference that happened from before and to after was that we were interested in one ion. So we wanted to see the quantum physics in one ion. So how the motion, you can create superpositions in the motion and things like that. And we never thought about more than one ion until maybe we discussed a little bit about that. But then when we heard the talk saying that you need many qubits in order to build a quantum computer, then it's an association of putting a qubit in an ion is very clear. So we said, well, we need many ions. So we have to start thinking about quantum physics of many qubits, many ions. And as Peter was saying, that's very simple to think of also how to do gates, single qubit, what is called single qubit gates, measurements. You can see that this system was already prepared for that. But the piece that was missing and the one that was kept us busy for a couple of months or 3 months was that how to make the ions to talk to each other. So how to make the qubits to interact, which is required for quantum computation. That was the main challenge, and the rest was almost there in the sense that conceptually it was very clear. Then let me tell you a story that I think that's very interesting. So we got so excited, but really so excited. We started discussing, and at that time I had to leave. I wanted to leave back I had to go actually to Harvard. Peter had to leave to Europe because he finished he got a professorship in Austria. But there was a week in which Peter was going to a conference in California. So the problem is that we could not discuss.
Organized by Steve Chu, and it was maybe more on the BC towards BC side. That happened also a year later. So we spent there a week.
Well, wait. I mean, because he was invited, and of course there was a postdoc, and I was not invited. It was very selected for. There was the Japanese American Association of Laser Physicists, something like that, and very few people were invited at the moment. Peter was very famous already, and so he was invited. And then, but we wanted to continue discussing, and so he smuggled me into the conference. So he said, "Well, just come. They have, have a room in a hotel. They have 2 beds, so we can be there." And so he was going to the talks, and I was waiting for him to discuss in the evenings. And so that's what we discussed. But at that time, actually, we were discussing how to build this quantum computer with atoms in cavities. So at the moment, so we were thinking these ions, but they don't interact with each other. So we shouldn't do that. We should think about atoms in cavities. And we were discussing a little bit more about quantum in cavities. So the conference was over. So we had some ideas, but it really didn't crystallize into something. And it was later on, because then I went to visit him in Innsbruck a couple of months later, 1 month later, where we started thinking about ions, and then again, so let's make them interact, and this is what came over. So.
One thing that is not that clear to me is, so the Feynman talks and paper, it's all about simulating quantum physics with quantum physics, right? So quantum systems simulating quantum systems. Was it already clear that the gate-based approach and this more abstracted computer science style approach was going to win? Or at the time, were you thinking, okay, do we make a gate? Do we try to make it more analog and like simulating some other system? Or were you already clear that gates are the way to go?
Well, the analog part came later on. Feynman showed how to build a quantum computer based on gates. And then people like Umesh Vazirani, I think that he played a very important role to realize that actually this quantum computer could be more powerful than classical computers. So Feynman was more saying, okay, let's solve problems in physics with that. But then Umesh Vazirani and some other people realized that this could be used for some other things. And so he developed the concepts of complexity. What does it mean more powerful? The theory. But it was on the table already that in order to build a quantum computer, you should be able to build these quantum gates, to have qubits, and to make them interact with each other according to gates. So this was the problem that was given to many people, how these abstract ideas can be turned into something that can be done in the lab. That was the question that Arthur Eckert asked.
So you were already operating with that as an assumption that we have to build something that will produce these like C-naught gates. Or
Exactly.
Maybe also mention here that there were these early ideas for quantum algorithms like Deutsch-Josa and so on that were very simple demonstrations that demonstrated that there was more power behind these things, and they were all phrased, of course, in this language with quantum gates. And so it seemed to be the natural sort of digital and then much more universal way of doing that. And this was the goal.
Yes. And maybe another point is that all these things were very theoretical until 1994. And so people knew that a quantum computer theoretically could be something that is more advantage, but there was not a practical application. So there was nothing that would say, oh, you build a quantum computer, then society will benefit from that. And that's what Peter Shor did. And in few months, and it raised a lot of attention. And this question, okay, so that's a theory. So how to do it in the lab?
And just a follow-up question, if atomic clocks didn't exist, would you be using the ion trap anyway, or were there other options that people weren't considering because atomic clocks were so advanced?
I think that the reason why AMO and some of the ions were somehow so successful that they had a big head start with all of that. The atomic clocks really, over these many, many years, and precision measurement in AMO is one of the core topics, of course, where AMO is very good at. So all of this work was done, and this whole investment done in a different context and could immediately be used. And of course, you can also use other system. And at that point, there were many other proposals also on the table. Most of them have disappeared in one or the other way. Well, there was NMR, quantum computing, all of these solid state proposals.
When we started, I think that around the same time, there was a proposal for doing this with NMR. This is in a molecule. You have different atoms in a molecule, and then the atoms could act as qubits that would interact with each other because you can just tune them using magnetic fields and some frequencies and so on. And there very soon there were some experiments, and the problem is that at the time this was not scalable. So this was done at room temperature. It was very clear that you could experiment with 2, 3, 4, but there was the end. That's where the ion traps had more advantage, because in principle there was a road to scaling them up and to make bigger experiments. And then a bit later, there were some other proposals on quantum dots, using quantum dots, and superconducting qubits, and photons were
this came so much later.
Photons with laters, and so they were just coming one after each other. And of course, so when somebody had a system that you can manipulate and observe quantum properties, let's say to control it at the quantum level, then it's a candidate to build a quantum computer with that, but it has to fulfill some other conditions. And that was not the good one, even though there are many in which we can observe these properties. It's very difficult just to tune them such that you can do the gates, the qubits, and so on.
Yeah, it's like too many candidates to pick from.
Yeah, but I would add to the story also that the ions also played a role because there was a certain concept behind it. With qubits, they were talking to a phone-on data bus, and so many other systems at the end somehow had a very similar structure. So there was a certain architecture, a certain way of doing it behind it that was then also could then be duplicated also in a somewhat different context. So in that sense, it was also conceptual what was going on there.
What's the structure you're talking about?
When you would like to do gates, for example, you have these individual ions that are storing the qubits, and you want to manipulate, like in our case, with the lasers individually. But this question that Ignacio talked about before of how to entangle, you need one, for example, collective degree of freedom that connects all of these ions together. And this was the phone-on modes there. And so the gate was basically that you have a qubit, and you write this qubit as a superposition state on your collective phone-on mode. So an ion which is somewhere else then sees the qubit motions for the first ion as the motional degree of freedom, but has in the internal state here in the second ion, and then you can locally manipulate these things to make a gate and then write it back. So this transfer of quantum information between the qubits and this phone-on data bus playing this role of that enables then to do these entangling operations.
How long was it from the conference until you had this aha moment that you could use the motional state as the quantum bus? And what else did you try out?
This was in Innsbruck. So we were thinking really about many possibilities, the ones that we knew very well, and trying to analyze with each of them how to do that and not to do that. And so at that time, actually, there was we were working on a project and another project, which was how to observe interference between two ions. But at that time, these ions were independent; they were not talking to each other. But we were discussing that the interferences were not that good if the ions will start interacting. And then the aha moment where we realized that, okay, interaction, so they can interact, so they can build gates with them. So the fact that there was bad for some other project, then we realized that could be used for the good to this particular project. And then we sat together and we put numbers and tried to think how to do this in practice and so on. And it was extremely fast. So I think in a week we had probably a paper written.
So, and I remember that we went to this first conference in Italy, Torino. So the proposal, the idea was ready, and then we were ready to present to the rest of the world somehow. And there was this conference in Torino.
The first thing that we did, of course, is to write to Arthur Eckert, because he was posing this question and said, we have an answer to this question, please have a look at it. And then he said, oh, that's very interesting. There's a conference next week in Torino, so can you go there?
Yeah, it had already started the conference when we contacted him, and so we just went there for 2 days, I guess it was. And so the idea came in October, and I think in November we went to this conference, and I remember that they were a very informal conference. Very few people, not like the quantum information conferences that we have right now. So a few fanatics, I would say, were there. And so we had the honor of being able to present this, and we gave 2 talks about this thing. And I remember that felt in the audience, somebody said, wow, something serious is happening here. But there was also a lot of questions. I remember that Sam Brownstein said, I have a mathematical proof that the gates that you want to do cannot work. Okay. But then we said, no, we are using just 1 extra level. And then Ian said, you're cheating. No, I said, no, that's atomic physics. It has more than 2 levels. So we're allowed to use that. And so sometimes you just look at it. That's right. There's a little bit a bigger picture behind it, and knowing some atomic physics might even help. And so we came back very enthusiastic, and this is where the paper was then written that we submitted, and then from there it was starting. Yeah.
But it was for us working in the community of AMO physics, always meeting people working on atoms and ions. And then all of a sudden we met a completely different community. These are the ones who were more working on quantum computation, but also quantum cryptography, foundations, Bell inequalities, and all that. It's a completely different community. And always when you meet a new community, it's very difficult to talk to them because you don't have the same language. And that's why there was some things that they didn't understand or we didn't understand, but it was very useful there to learn now the real motivation, not only to factorize numbers, so there were some other motivations for quantum computers, and also to get to know the community. And from then on, I think that we were now very well accepted in the community. And so we went to more conferences and learned from them a lot.
But I think we should also add that at that point, it was not that everybody got immediately enthusiastic about quantum computing. There were a lot of people that were very critical of the situation, did not believe that it was meaningful to build a quantum computer, that it was feasible to build a quantum computer. Serge Haroche, for example, wrote a comment in Physics Today, and I think that's very important that there's critical voices in this context that was very critical of the whole situation, and that we're wasting our time as physicists is something that maybe at the end doesn't work, there's not a deeper meaning. But
what was the main criticism? Just that it's not possible to build it, or?
Well, there was a paper written in physics which was called A Quantum Computer, a Dream or a Nightmare. Meaning that, of course, it's fantastic, but on the other hand, if you start making a lot of noise and thinking that now physics should be devoted to build a quantum computer, where there are many other things to do in fundamental physics, it can distract us, and that at some point it may happen that it's even impossible to build a quantum computer. So one of the claims of that paper is that may be really impossible. And the reason is it was very clear at the time that what they were saying is very, very serious. And we notice it now, that if you have errors in your quantum computers because things are not perfect, then this exponential speed up that you get thanks to quantum computer, there is an exponential, let's say, damage made by decoherence, and they compensate each other, so there is no gain at the end. And so they were claiming that, and it was very clear. But around the time where this happened, then the paper of error correction from Peter Shor came up. And then he showed, yeah, it was very timely. And also, it was extremely important for quantum computation because with that, of course, it would have been an entertainment, no, to think about that, but never feasible.
And was it clear from experimental point of view where are the main problems of the decoherence or the errors, where the laser should be tuned or the ion traps need to be more optimized? Where were the main issues from the experimental side? Like
we had it in our paper. So in our paper already, when we wrote, we identify the causes of decoherence. And so we said, okay, so first was the atomic motion. So these qubits, they communicate with each other through this common bus that Peter was talking about. So this common bus is just the motion. And the fact that they move, if they lose this motion, so if they lose phonons, for example, then this would be the
there
main...
would be heating, for example.
or
things like
heating, and so this was the main question there. But there are others that we enumerated.
And I think that we should also add that Dave Wineland was actually the first one to the first quantum logical gate, which was not the complete story yet, not between two ions, but it was between the ions in the phonon data bus that they did a gate. And this somehow added a lot to believing the whole story. So then it was much more trying to put now things together. And so Dave Wineland here deserves a lot of credit for doing that, together with Chris Monroe. He was then a postdoc in his group. But of course, the big challenge was then how to scale it up. And really, and this took, in my opinion, much longer than I personally expected. I would say that they had these ion strings in there. They just go there with the lasers and do it. But this was then, of course, a little bit naive. And this took then really much longer. But at the end, it happened. Yeah.
So we hoped at that time that these sources of the coherence could be improved, and because the people have done a very wonderful job with atomic clocks, and in the same way some other sources which were important maybe, but it was extremely difficult. Actually, experimentalists did, not only Dave Wineland and Chris Monroe were the leaders at the beginning, Rainer Blatt and some other people did experiments, improve, and then at the end, so now we have now these prototypes of quantum computers. I mean, they're still not big enough, but I mean, they really managed to overcome some of these problems related to the.
So one should say that sort of these next generations, there was also Rainer Blatt in Innsbruck, and we had the benefit. I moved back to Innsbruck, and then Ignacio came to Innsbruck, where we did all of these things. I was then a professor in Innsbruck for a while. And Rainer Blatt, that we had gotten to know at Chile, he then also moved there, and he's put it on his flag that he wanted to do now this trapped ion quantum computing. So there was a very close connection here in the experiment. And I think that in retrospect, it was really Dave Wineland, Rainer Blatt, Chris Monroe, who were the ones that developed this whole thing in the way that we know it right now, even though, of course, now it's much broader.
Because Wineland and Monroe were surprisingly fast in publishing their first demonstration. Did they already have all the trapped chain in the lab?
I would say they built an atomic clock, and the ingredients are the atomic clock. So if you do it on the level of a single ion, they had ground state cooling. They knew how to manipulate with this laser. So all of the things that we had talked about were motivated, but on the other hand, they were also available in the lab right away. They did the first demonstration of these quantum logical gates just a few months after we wrote our paper. Yeah. And this was then the starting point. So this first step was easy, but of course afterwards then these other developments of scaling up and then having more ions, which then led to these teleportation experiments and so on. This took then a few years, but they happened. And there were other difficulties then, of course, which is finite temperature, for example, of the phonon motion, that we never really cooled to the complete ground state. And then other people came up with variants of the gates. We worked on high temperature gate, but it was really Klaus Möllmer and also Anders Sørensen that came up with their version of the gate that we proposed by going off resonance that was then insensitive to temperature. We had originally, we made the assumption, well, we can cool to the ground state, which was true, to a large degree. I don't know, 0.99 or whatever percent that you can do in this context. But at the end, this motion of the ion, there will be errors due to the fact that on one hand, it might be heating up. On the other hand, the initial state that you had might not be a pure ground state. And we had assumed this thing in our context. And then the challenge was to develop now versions on the gate based on this toolbox that we had that were insensitive to temperature, that you had some motional degrees, that was a density matrix, was maybe hot. And then you do a gate, but at the end, sort of the qubits, the quantum memory factorizes out and leaving behind then a collective quantum state, which is in your collective phonon data bus that can be still hot. So the challenge was with a hot data bus, nonetheless being able to do entangling gates. And several versions, we proposed one, and the famous Möllmer-Sørensen gate was another way of doing that. That sort of is a variant that at the end is how the people are doing this thing at the moment. So it's a variation of the theme, I would say. Yeah.
How does it work?
Should we now talk about geometric gates, Ignacio?
Yeah, the basic idea is that in order to get a gate between two ions, then they have to talk to each other. And so you can imagine that the two ions have some Coulomb interactions, and the Coulomb interaction depends on the distance. So if the ions are more distant, then they have some Coulomb interaction, which is different if they are closer. And now this Coulomb interaction energy, this energy, gives you a phase. And these are the phases that appear in the gate. So this means that if you're able to put the ions in and change the distance depending on the state of the qubit. If it's in 0, for example, they don't move, and if they are in 1, they will move. Then the distance that they have depends on the qubit, but now the phase that they get, which is related to the energy, is different because the distance is different. And so that's the basic idea. So that to make the ions get different phases, this is the quantum gate is about the phases that they get depending on the qubit. And because of the distance, we transform the qubit into positions. Positions give you distances, and the distance give you different phases. And now the point is that if they are moving, this is what it means if they have temperature, it doesn't matter because in average they see the same Coulomb interaction. So if they are at a bit different distance, then there will be some fluctuations, but the average is the same. And that's why they are not completely immune against motion, but they are more robust against motion. So this was more or less the kind of back of the envelope.
With laser beams, do you induce any dipole moments?
Exactly. So with lasers, what you do is that depending of the qubit is in 0 or in 1, then you move them. If it's in 0, it's here. If it's in 1, you push them away. Now, if this is in 0, it's here. If it's in 1, you push them away. So now you see that if they are 0, 0, they are at a distance. If they are in 1, 1, they are a distance. If there's 0, 1 here and 1, 0 here. So you see that the distance depends on the state of the qubit. And therefore, the phase that they will acquire, which is related to the energy, to the Coulomb energy that they will have, will depend on the state of the qubits.
Why does it get pushed away depending on its state?
Oh, because these ions have some dipoles, like little dipoles, and the light pushes them. Yeah. And so depending on the internal state that they have, depending on whether they are 0 or 1, they can get different dipoles, and so then they can get pushed in a different way.
Do you have a gradient of electrical field additionally to exert that force? Or?
You could do it with a gradient, for example. That's actually one of the things that we proposed many years ago, many years before, that you could push these dipoles with a gradient, just having a standing wave that has a gradient in intensity, and this will push them. But there is an alternative way, which is basically to push them sending photons and having a recoil. So whenever they absorb a photon, then they will push. So then if they are in a state where they cannot absorb photons, this is the 0, they don't push. If they are in a state where they can absorb photons, then they will be pushed. This is 1. And this is how they are pushed depending on the state of the qubit. These two methods are basically equivalent if you write them down, but they are the two methods that people use.
To my mind comes also the neutral atoms as well. Well, it's maybe a different mechanism, but it seems like you excite the exchange of dipole moments and then it jumps out.
Actually, we wrote after this ion trap quantum computer, then we started working on some other platforms to build quantum computers, and we thought about how to do it with atoms down in cavities, first of all, but also atoms that are trapped in optical lattices, and using the same basic ideas that depending on the internal state, you push them, and if you push them, then you can put two of them in the same position, and then they interact with each other. And so actually we wrote a series of papers, using different...
At the end also the Rydberg excitation, so what's being used at the moment, with the tweezer arrays that we have, that Misha Lukin, for example, does so successfully, or Antoine Prouvé, and several other people. The younger generation, this idea of taking an atom, we always thought about in a set of the tweezer array to have them stored in an optical lattice. Tweezers at that point did not really exist, and we wrote this paper about fastgate. We introduced the dipole blockade mechanism, and this was also the point of connection with Misha Lukin, because we found out at the end, we already had a draft ready at that point, that Misha was working on very similar things and had similar ideas. And then we simply said, you have ideas here with little atomic ensembles. People think about quantum gates. Why don't we put this thing together and work and collaborate? So I think it also expresses a little bit the spirit that we have in the AMO community, that we might be fierce competitors, but at the end of the day, we collaborate. And I think that this collaboration, this in the AMO community, particularly in this context, this was
very supportive.
Yeah. Because our names appear in some of these papers. Many of these papers were written with many collaborations with some other people, and particularly important when there was with Misha, Michael Fleischauer, Robin Cotte, so people on the Rydberg gate. And
something is bothering me still from like half an hour ago. You mentioned that there are people proposing to do quantum computing with, let's say, some molecule with multiple atoms in it. I think it would be very instructive if you can explain why is that a bad idea, besides the fact that atomic clocks already existed. But what are the challenges? Let's say you were going to build an arbitrary molecule and start somehow, I guess the question is how do you communicate with different parts of it? But
it's a great idea, and the question is that the practical implementation is what it's difficult. If you had an isolated molecule, just one molecule, and then you could make the atoms interact with each other, then the limitation would be the size of the molecule, plus what you just said, that maybe if the atoms are far away, then they don't interact with each other. These are the nuclear spins, then they interact with each other. But the problem is that you don't have these molecules isolated, they are in liquid. And so they're interacting with each other, and they're at room temperature. This is what is called NMR. And so the idea is that what you will have is that they are completely, all these spins are completely mixed. But since there's that many, or there are 10 to the 20 or 10 to the 30 molecules, then they figure out that effectively you could see some of the degrees of freedom, and then you could see how these even individual molecules would interact, even if there is a lot of, let's say, dirt in the back. That was the great idea, that despite it's a liquid, there are a lot of decoherent. Then you can collecting a lot of data, and out of this 10 to the 20, then you get a signal which is very small compared to the noise, but you can get something. But then it's very clear that it doesn't scale. So you want to make it bigger and bigger and bigger, then the signal goes exponentially down. So with the size of the system, then the signal goes exponentially down.
When you say bigger, do you mean
more atoms. You want to build more qubits in a single molecule. So you want to just now have more qubits and qubits, which we need for quantum computation. Since the signal goes exponentially down with the number, then at the order of 10 or 12, then you have no signal, so that's not going to scale. Because now what you can say is that, okay, let's forget about the liquid, and let's isolate one molecule and do it with one molecule. And that's another thing that people work for a while, but that's much more difficult to have it. Or you can have a molecule just embedded in a solid, and then maybe the environment of the solid. Well, this could be like, it's a different story because color systems are like atoms, but then people thought about doing this NMR with single molecules now embedded in some other environments that would be protected. But at the moment, this didn't compete with the other technologies that we have at the moment.
And was there also NMR idea used for ions as well? Because you can induce like magnetic moments and then use magnetic fields to do similar types of motion. Or electrical field.
But are you saying in order to make them interact or so, this type of magnetic dipole moments would be very small over this distance?
Yeah, I somehow found online there was some explanation of how to use ions as magnetic dipoles. I'm not sure. Maybe it's a different approach to leverage it.
I think that in the ion trap quantum computer, then there have been now some other ways that people have figured out how with ions you could do quantum computation. One of them is using magnetic fields, actually time-dependent magnetic fields. And so that's the proposal that we, with gradients of magnetic field. And so people are trying that, and this is a very serious alternative to the things that we propose that people are doing with lasers, but they are not at the moment at the level of the other setups.
But the workhorse is the same as you described back in 1995 is the same up to these days.
One should maybe add that with the NMR, of course, these are always on interactions. So you might get entanglement between these atoms that constitute your molecule. But with the ion, you have the big advantage that you have a laser where you can switch these things on and off and really do the gates. This is an always on interaction. And then, of course, the whole scenario of doing then gate-based quantum computing without the control of switching on and off is something that has some corresponding overhead, so it makes it more complicated. So in this sense, the ions were to some extent also conceptually a more clean system, and therefore if a laser, switch it on, this is how you do the gate, and then you switch it off, and then it sits in memory. And with NMR, that's much more complicated.
Do you have a personal favorite paper of yours that you've written together? Is it the C0 gate paper, the original one?
Well, we wrote so many papers together, actually, in different contexts. I mean,
Maybe for the interaction, was there one that particularly sticks out?
So if I look at my publication list, the highly cited ones, there's obviously his name Cirac somewhere.
Yeah, that's the same happens with mine. So I think that was very... So we always collect memories from the time where we were working very closely and developing all these ideas. So there was this ion trap, then there was this collatoms in optical lattice for analog quantum simulation or quantum repeater. So there was some, for the young audience, it's important maybe to know that at that time, it was very different from now. Things were to be discovered, so that people didn't know anything. So whenever you step on a stone, then there was something, some idea coming up. So we had many discussions, many ideas. We didn't have time to work on all of them because they were really appearing one after each other. So it was very creative times, and because we're very, very lucky that the things were to be discovered.
So one should maybe add that 1995 was also a very special year, both science and condensation. So we thought a lot immediately can be benefit from BEC, this whole context. They're very cold atoms. Of course, they are a weakly interacting gas. They're just the opposite of what you want. What are the qubits? The BEC is just the opposite. All of the particles are in one wave functions. This is not a qubit. But then this idea came up that you store them in optical lattices, you do a Mott insulator. This was interesting from the point of view of condensed matter physics with cold atoms, because you make a BC strongly interacting by putting it into an optical lattice, and you even have a knob, which is the depth of your optical lattice to control that. And then you see things like quantum phase transition. So it's getting much more a story of condensed matter physics and doing the new kind of condensed matter physics with cold atoms that are strongly interacting. And this gave then rise to the quantum simulator part. But we also had ideas at the same time that once you had all of these atoms stored individually, like in a mod insulator, exactly one atom at a point, to the extent that you can address them individually, which is happening now, but then early in the game, this was experimentally very, very difficult. That this could also be a source of quantum computing. And we wrote some papers about these spin-dependent lattices and doing collisional gates. Some of these things happened more or less afterwards. Emanuel Bloch played an important role, Markus Greiner, Tilman Esslinger, with this seminal experiment of showing this mod insulator. But they took much more at the end this analog quantum simulation route and not so much the quantum computing, even though ideas were around. But the experiments were simply not developed at that point, at the moment, needing local control and local readout. Many of these things are available right now. When we have the quantum gas microscope, we can observe single atoms in there and read them out. These fantastic experiments that reveal all of these different spin patterns that you can distinguish in different phases that you realize and so on. And we thought about using some of these ideas for quantum computing, but went a little bit more the other way.
So maybe also related to your question, so this ion trap quantum computer paper, this quantum simulation paper, the quantum repeaters. But there was another thing that I think was very important for us, where we started thinking, so what happens if your quantum computer is not in a single set, but is distributed? So you have one in one place, another in the other place. So how can we communicate qubits that are far away? And so that's why we wrote some of the papers at the time with Jeff Kimball, actually, who's in KITP. The idea was that people knew that with photons, then you can have quantum communication. However, we thought at that time that these photons disappear, so you would like to have a memory where to store them because you want to use them and also purify to build quantum repeaters. But how can you convince two atoms to get entangled at a distance? And so, of course, it's clear that one atom can emit a photon, and this photon can go to the other atom that can be absorbed. And in this way, you could entangle them because then like an effective interaction. However, it's very difficult to convince an atom that emits a photon that goes exactly to an atom that is many kilometers away. It is absorbed. And so the challenge, the theoretical challenge at that time was to see how you could convince a photon to go. And then so we use ideas of cavity query and something that
so
were
we
on the
wrote this
market.
paper at KTB, remember that we were there for 3 weeks or whatever. And somehow we came there, this is what we should do. And I think within a few days we had somehow an answer and then very beautiful results. And then Jeff Kimball came and Hideo Mabuchi and we wrote this paper there together.
But this is, I think, that what we meant before when we say that, of course, you just woke up in the morning and say, what would be the next thing? Okay, they're at distance. What is the next thing? So let's maybe with some other one, another. Maybe simulate now analog, not like Feynman was saying. So with many things appearing, let's say, now it's much more difficult to do research in this field because many of the ideas have been developed and so on. And now to make advance is more difficult than at that time. The forest was completely full of trees and they benefit from that.
It happened at KTB that this probabilistic entanglement, right? That normally, so what Ignacio described before is this, that you got an atom, which is quantum memory. It's a stationary qubit there. You put a cavity around, and then you come up with a protocol where this photon gets emitted as a wave packet, and you find a protocol that there's an atom in the second cavity over here, and you have to do it just right that you catch it 100 this quantum state transfer. But then the other idea, remember the drawings that we had down there.
Maybe this exemplifies so the way that we were thinking and some of the people thinking at that time. So we knew how you can send one photon from one atom to another one, but that's very difficult because the light in the cavity may be reflected. And so then we say it's very easy for photons to come out from cavities, but it's very difficult to convince them to enter the other cavity. So can we make a gate just with photons just coming out? So that's the way of thinking, which is the simplest. And yes, if there are photons coming out from both atoms, then they can interfere. And if you measure, they get entangled. And so that's the other way.
And this is now the workhorse, I would say, for many of these, at the end, and even quantum repeater ideas and all of that. This somehow led to that. And this is the way at the moment how to do it, because in this probabilistic entanglement, the great advantage is that you may try and you may fail, but at one point where you got the right kind of measurement, now I have an entangled state, and then so this is then producing EPR pairs like in the factories, and you put them on hold when you need them, and then you can purify them and use them for teleportation, and this then makes this connection of connecting quantum computers and in a sort of a global or maybe local network, and it's a way of scaling up quantum computers.
So it seems like you were also very closely following what the experimentalists were doing and what was possible. Have you ever proposed something where your experimentalist colleagues said, oh no, like that's clearly a theorist's proposal?
My personal experience is that I'm really amazed to know what experimentally can be done and about the power of these experimentalists. Of course, when you talk to your experimental friend about some of these ideas, they come up immediately with a lot of complaints why this is hard to do. But if they really want to do something, really want to do, and there must be motivation behind it. And building a quantum computer is actually a big motivation. They're able to do miracles. So when experimentalists tell me this is very hard or impossible, okay, let them complain. If it's really important, they will figure out a way of doing it. So my compliments to experimentalists.
Yes, and maybe not only that, because when we have some ideas of how to create all these things, so we could think of a specific way of doing it. So one thing is the idea, like a more abstract idea, how to do it. But then one can say what kind of atoms, how should be the levels and so on. And then we soon realize that when you are very specific, experimentalists are much better in doing that, so that they can really find what are the real way of doing it in practice much better. So it's good to have, as a theorist, an idea of how to do it in practice, but the details of that experimentalists are much better than we are.
Have there been instances of where you were surprised where experiment was already at, where they were able to do certain things and you were like, oh, wow, we thought this would be much, much harder?
Yes, this has happened. The first, what Peter was mentioning, with the first experiment with Dave Wineland and Chris Monroe on this demonstration of a quantum computer. This happened soon after our paper. We thought it was visionary or futuristic, but this happened soon. But it happened several times. The multi-insulator superfluid transition.
Yeah, this also happened, I think, 3 years after our proposal. It happened in the lab. And
Wow, they were really motivated to do that. Anything else? What surprised you in the field? Because you have seen it from 1990s and now it's going. 30 years have passed, and what was the brightest memories from what surprised you or shocked you? Or
what was amazing, has been amazing the last years, is the Rydberg atoms. So how they, in 4 years, they came from something with a demonstration to now one of the, let's say, leading technologies for quantum computation. This has happened very fast and extremely precise. So that has been very positively surprised.
And for us, it's sort of fascinating. We started with AMO, believing that AMO, is a very good way of doing that. And now 30 years later, we have these different AMO platforms from the ions that are maybe doing the most high fidelity gates, like Quantinum, for example, what they have. But now the Rydbergs, they really seem to scale better than some of the other systems. And of course, we have the superconducting qubits that we always consider to be honorary members of AMO. They got artificial atoms, okay. They got artificial atoms there, but somehow, so all of these different platforms, they have taken a certain lead now, and I think that there will be a time window. Depends how long it is. AMO systems, of course, are slower than some of the other ones, like superconducting. So at the end, of course, speed at one point will also matter. But I see now there's really an opportunity now, a time window where AMO systems are really among the very, very leading platforms. And it's interesting to see that after 30 years, that it really developed and happened in this way.
Let's say if you were going to today rethink this, right? Is there a way just to make a quantum computer with simple silicon chips?
Michelle Simmons is looking at this, right? With implanted phosphorus.
If you think about it just from a practical level, that would be ideal, right? So the atom computers are beautiful, but the ideal case would be like no change. Just send the design to TSMC and you get your quantum computer.
They can fabricate it with
they just fabricate it with a standard approach. At least on a physics level, on a theoretical level, is there any way to build something like that you guys have thought about?
Yes, well, not this was not our idea. This was other people's idea. First of all, they can use quantum dots in silicon. And then, so that there are experiments doing that, and so they are very advanced, so they're able to see several qubits and to do some qubit gates. And the original thought is what you just say, so then it would be a very simple way of scaling, because you can do one, then you can do a million. Now, the problem there, or they say the current problem, is that they have to be identical, they have to be the same. And so it's very critical for a quantum system. So your qubits, if they're different, they will not interact perfectly. And exactly, that's the advantage of atoms, that the atoms is more difficult just to build a million of them or to have a million of them. Those you can artificially create them, but the fact that they are not the same and also that they have some solid state environment, so they're completely interacting with phonons and so on, makes it difficult. It still is a very promising architecture, and so it's not only now quantum dots, but what you mentioned with the phosphorus implanted in silicon and some other ones, then people have done demonstrations and they're catching up, and so it may happen that that's a technology that takes over in the near future, so it's very promising.
Is there a way to analyze it like more theoretically? For example, is there some limit that you hit if you're in a solid state crystal that's impossible to overcome, or like some noise sort limit or something?
This relates to the question before. So if we were in 1995, now they will say yes, and there is some fundamental reason why you will never be able to scale, because you can never make the noise smaller than something. But since now we know that there is error correction, then there is just some level of noise that you have to reach, and you can scale just keeping this level of noise, and you can build anything you want. And so the goal is not just to be able to be infinitely precise, but rather to reach it. You have to just reach a level and be able to scale just keeping this. And that's not impossible with any of the technologies. And that's why we have many horses now running in parallel, trying to get this level of noise to scale it. And if they're able to do that, then they will be able to scale up.
I would like to add sort of one part about this discussion, AMO physics versus solid state. And I agree entirely that in the long run, solid state ideas will be a big contender in this whole thing. But the philosophy is also this, that when I talk about a single qubit, what you do in AMO and with ions and atoms and so on is this, that you got an atom and you take an electron inside of the atom, which is your qubit, and you can manipulate it with a laser optically, or maybe with some microwave, whatever it is. But you would like to keep this atom isolated. And what we do in AMO is this, that we build traps, electromagnetic traps or maybe laser traps, and we keep a single atom completely away from all of the decohering environment. What does a quantum dot do? A quantum dot takes a solid, and the only point of the solid there in the quantum dot is that the quantum dot is there next morning when I come to the lab and I turn it on and it's still there. So it's sort of like having a trap, but this trap, the other parts of the solid don't really play any functional role in these things. Maybe you can design some of that. That's right, yeah. So to some extent, AMO really does the pure thing. You take what you really want, this electron, which is held in an atom, that gives you the way of manipulating that, and then you want to remove the environment and just keep these things there that you really want, which is your isolated qubit. And that's a success and the reason why AMO has taken on a leading role. And I have no doubt that at one point, solid-state physics will come up at the point where they can control these solids in terms of temperature and all of that and perfection and so on, that this can also be done. But I'm saying that the only motivation to do solid state is that it's very convenient that they're there the next day, but it comes also with a hefty price to pay. If you're able to manage that, then I agree entirely that this is a way of scaling up that may be much more aligned with the traditional way how the industry works in this context. But AMO really does the pure thing. This is the.
What about going in the opposite direction? So this is probably an even stupider question, but can you have multiple qubits inside one atom? So for example, using multiple electrons, using the subatomic particles, I don't know. Can you make a quantum computer out of just one atom with 1,000,000 qubits, for example?
Okay, so what you're talking about is that sort of maybe a little bit back to the NMR question, or that if I take a complicated molecule.
No, just one atom. If you go subatomic.
Well, but then you got the linear Hilbert spaces. You know, the point with the qubit and the scalability is really I have one qubit, which is two levels. Then I have 2, and then 3 and 4, it goes exponentially, the Hilbert space. And I'm able to manipulate them individually, and all of these ideas about error correction are developed for qubits. And what you are now saying is that you got some other huge Hilbert space, but you really get the control. For example, you might simply say, I got a single atom and I got this Rydberg series that goes up. Yeah. Why not use all of them as a qubit? But that's, of course, the linear Hilbert space. But then the number of lasers that you need in order to control all of that also goes up exponentially. So there's the wrong scaling. So what you say is right, but it's on the other hand also wrong, you know.
You need a special laser for that.
Well, you need many lasers, so I don't know many
wavelengths. Yeah.
So the scaling of the resources to manipulate it, you know, becomes then very tough.
I think with AMO, another big advantage is that you don't have to do that much wiring. When it's solid state, it's like set in stone.
Well, your wires are your lasers that you're shining in, and they are very flexible. Okay, so
yes, they are much flexible.
That's right. Yeah.
Yeah, so you were mentioning earlier that it's becoming harder and harder compared to the early days to research in this field. And do you think, maybe a somewhat heretic question, do you think that quantum computing has become an engineering quest now rather than a physics research topic? Or what is your opinion on that?
Quantum computing, now there are many areas, and some of them are engineering, but some of them is really still fundamental science. Just let me give you an example. So if you want to scale up now superconducting quantum computers, you will have to do a lot of engineering, and it's very important that you do this engineering. If you want to find applications of quantum computer, then you have to find new quantum algorithms, and we have very few. You want to scale up also not from the hardware point, not only from the hardware point of view, you will need better error correcting codes, and that's also fundamental science. Maybe you want to protect the qubits in a better way or design new qubits which are more protected is fundamental science. So I think that there is even at the moment, there are a lot of questions which are related to fundamental science if we want not only to build these computers, but to use these computers. But it's clear also the engineering part, so it's a combination of both.
I would add here that, once engineers are taking over, then it means that the physics is done of having settled that this is a way of doing it, but then you somehow freeze it and trying to take this concept, what you have, and make it better and better and better. But I would say that in physics, we are still at the point where things are very much open. So there may be another idea out there that is much better what we have at the moment. And I think we should be open to that. And there's a pretty good probability that, there will be better ideas out there. And so in that sense, I think it's not engineering only.
So some people make analogs with what happened in the past. For example, when they built the first classical computers, they were based on bulbs, but there was a breakthrough, which is a transistor that was discovered later on. And so maybe there is something to be discovered like a transistor, the equivalent of transistors for quantum computers that makes things better and more scalable. And they will not come just from engineering, they will come more from fundamental science. So that's why there is a lot of room for science, basic science still.
The comparison to classical computers is actually quite interesting. When you look at the history, what are the similarities, or has it developed very differently?
That's very interesting. I think that there are very clear similarities. And one of them that I like it a lot is that now if you ask me, why do we want to build a quantum computer? What are where we are going to get advantages? And I will tell you that we have basically two applications where it's very clear. So one of them is in cryptography, actually to decrypt messages. And so that's one of the clear applications of quantum computers, to hack, let's say, communication. And the second one is to study chemistry, so to study physical systems, to simulate systems. And these are the two clear applications. There are some other ones which are more speculative, related to optimization, related to machine learning, but these are the ones that we know where the quantum computers will help us. Now we go 80 years back, when the first classical computers were developed and were built. They had two applications mainly. You know which ones? To break messages, okay, because they were the Second World War. And second, to study physics, because they wanted to solve differential equation physics. And at that time, they didn't know all the applications that we have right now. So we hope that this history develops in a parallel way, and that we will find many other applications once we are building these quantum computers.
What are the upcoming milestones if we look into the future? What is going to happen maybe in the next 5 years if we...
Or what do you wish? What do you wish to happen?
I'd say it's actually very clear for me what Misha Lukin does at the moment at Harvard. He's taking the lead now when it comes to this error correction, fault-tolerant quantum computing. There will now really be an era where sort of error correction can be done seriously. This implies scalability to all of that, and then we have really fault-tolerant algorithms. This means scaling up the system, which is then very much an engineering job in many respects, but also maybe too much even of an engineering in this context. So I would say that entering this era of fault-tolerant quantum computing, this will be like a phase transition in the field where it really gets serious. And I think that once you have that, then, many ideas that we think at the moment, where we are limited to gate depths that are very shallow and all of that, this will open the door to many of these other things that we have been dreaming of. I think it will be very similar to what we had in, for example, artificial intelligence. Many of these ideas that we now use in ChatGPT or whatever it is, were around in principle 30, 40, 50 years ago, but there was no hardware to do that. And then it somehow became dormant, but the hardware developed. At one point, there was the threshold where these things happened, and they work actually in a much better way. And I would, again, to make this analogy with Ignacio, I would expect that we will also enter a phase where this hardware needs to be developed, but at one point, there may be surprises how well these things work, and some of these early ideas might then be realized. in a way that really will change the world.
And both of you are also involved in commercialization of quantum computers. How involved are
Yes,
you
so
and what's your experience?
There's actually maybe many companies now doing startups, and with the INs, there's of course companies like Quantinum. Chris Monroe has a company, INQ. And in Innsbruck, there's actually AQD that my colleague Rainer Blatt and Thomas Mons founded, and I'm a little bit in the second row in this whole thing. This idea of making this thing commercial is, of course, very early when it comes to finding the real applications or so. But I think there's a transition happening to this industry of what usually fills the whole room with a quantum computer, just a challenge of putting it now into a rack, that you can move around and use and so on. This is, I think, something very important and sort of part of this engineering job. We are not at a point where we can sell now big quantum computers, and I think that the rest of the world to fulfill these promises of doing big quantum chemistry calculation or maybe optimization, the stream of doing optimization. But I think it's condensing experimental apparatus into one rack, okay, and this can be a game changer. Yeah?
And what do you think matters for this quantum computers as a product? So you mentioned that there's error rate, like decoherence, fault tolerance. Is there anything else?
So it depends on the market that you want to address. So they say if you want a fault-tolerant quantum computer that would do everything that a quantum computer is supposed to do, then there are many challenges. So that's scaling up, errors, decoherent, maybe even new applications, because there's no market, because we mentioned the two applications that exist, so people have to develop more. That's one very clear things that should happen in the future. But there's the other part that it's getting very interesting, which is more about quantum simulations, so a quantum computer which is dedicated not to solve arbitrary problems, but just to solve some particular problems related to physics, for example, design of materials, solving some equations that appear in high energy physics. And that's something that requires a bit better improvement, but maybe not so much error correction. So that's another field that is taking off, and may happen that there's even commercialization. Of course, it's not the society or the typical user of a computer doesn't want to solve a problem in high energy physics. That's very clear. But if you could just have in computational centers or big computers, you could have a part that is, let's say, on the side there is a quantum computer or quantum simulator that solves this problem. This may have a market as well. And so you see, there's not just a single idea where things have to evolve. Even from the commercial point of view, there can many areas.
But maybe I can add one part of here. I mean, as you argued, was that there's sort of basic science that becomes then a technology, and then it has economic and social consequences and all of these things. I think we should not forget that these ideas of having somehow quantum machines that can be really manipulate entanglement, all of these things will also feed back actually to basic science. And I think a very good example in my mind is actually quantum metrology. The ions came out of atomic clocks, were built on that, were expanding that, it became a quantum computer. But these entanglement capabilities, they are now going back to basic science, and maybe then also the element of some completely new discoveries in physics, because based on that, we might be able to build now quantum sensors that are much more precise. Hopefully we find then even some new physics. Think about just LIGO by having entangled quantum sensor networks up there, maybe as a better way or another generation of doing then, I don't know, gravitational wave detections or studying the interface of general relativity with quantum physics. So this basic discovery that can be done in this context, enabled by these techniques, like classical computers came back into the lab and now take over a lot of these things and just are a basic tool. I think that the same thing might also happen, or will happen, I would say, that with the quantum computers. So they will be a tool for fundamental discoveries in physics.
Yeah, actually, that was one of my questions that I was waiting to ask, is basically, if you look at like the Crookes tube 120, 130 years ago, there's people found X-rays by accident, essentially. If you had to guess, what would be like an accidental basic physics discovery?
One of the interesting things that could happen is that quantum computers don't work, because quantum physics is wrong. And so we discovered that quantum physics is wrong at some level. This is very, very unlikely, but that there would be a way of discovering a theory that goes beyond quantum physics.
And how would we see this? As like a persistent source of error, or like a behavior, unexpected behavior.
For example, there are some theories about collapses, so that when you go to different sizes, masses, and also Penrose, for example, has a theory that there is a spontaneous collapse of wave functions. This could happen, and maybe this be discovered. I think that even if this happens, quantum computers could be built, because we have error correction that could even correct the errors that are not quantum physics. But anyway, that could help us to discover a theory. Another thing that now it's actually, we're participating in a workshop here at the moment, so that's why we are here, in which people try to see, one of the subjects of the topic is how quantum computers can help in quantum gravity. As you know, quantum gravity is something that does not really exist. We don't have a quantum theory of gravity. But there are some questions that cannot be addressed because we don't have computers in that context, that cannot be addressed because we don't have sufficiently powerful computers. And if we had a quantum computer, then we could address some of these questions and help to maybe discover or help to develop a theory of quantum gravity. So we see that, well, as Peter says, so technology may come back to help science in order to advance, not only by discovering, let's say, unknown things that we don't know, but also to make some things that we cannot do with current computers. And
I think we should add that this is a perspective that we, as sort of people coming from physics, are really excited about. It's very nice that there's commercial applications, people are making money, startup companies, but to see this thing come back to science and then enabling some new physics, this is maybe even closer to our heart. Yeah.
With gravity, if you take the same ion trap or neutral ion, whatever, the same atomic computer, and let's say you operate it on Earth or operate it in space with low gravity, is there a theory of quantum gravity that would be consistent with something detectable there, or like some way of...
No, it's more about equations. You want to solve at the end some equations, and they're too difficult for classical computers, and this equation will tell you something about quantum gravity. And we cannot say something about quantum gravity in some specific context because we cannot solve this equation. If we had a quantum computer, we can solve these equations in a much more efficient way, and therefore we'll have a handle on that.
I guess my question is just, if you take a quantum computer and you operate it in space, is there a potential for a surprising result where you can somehow, in one of the theories of quantum gravity, it would imply one thing, another theory of quantum gravity?
There is one example of that. You'd have a computer and a quantum computer, and then you are thrown to a black hole. And you enter a black hole, then people are speculating that then you will be able to do maybe computations that are beyond what a quantum computer can do. Unfortunately, you could not tell anybody, right? but that's something that people are thinking at the moment. Yeah, not the gravity that is outside, but the big one, the one that you have in a
Deploy quantum computers to space.
Yeah, I mean, what's the smallest quantum computer?
One of our questions that we like to ask, if you had infinite financial or human resources, what would be the project that you would love to do or tell maybe your experimentalist colleagues to do?
Infinite resources. Yeah. Well, I would say that, and it's on my side, I think that we are limited our brain maybe more than the financial constraints at the moment. So there's a lot of funding out there for all of these quantum things, and there's all of these technical developments that need more and more money. But the kind of things that really feel as the deep open questions, I think it just takes some brilliant minds. And I think that this is also happening because different communities have merged together. Initially this quantum computing started as something very small, but now when you see some of the big conferences and you see new communities coming in, from computer scientists to mathematical physicists, people working on quantum gravity, this is so enlarging, and now all of them speak the same language. And so I think that sort of to fund this community, and this is what's happening at the moment, this is, I see as one of the most promising developments. And if quantum information played a role in all of that, it's now a common language and a common way of thinking across different communities that so far have been very disconnected. And I think that this is one of these consequences and all of that. And yeah, it needs money because this community need to be funded, but I think that the frontiers of physics have always been funded. So I would say we are maybe more brain limited than money limited at the moment. But of course, engineers consume an infinite amount of...
Yeah, but that's a good question. So could there be a Manhattan program or Apollo program and quantum computer that you say, we put many scientists, engineers, let's say, in some place, and for sure there will be an acceleration in the development, but it's not clear to me that there will be a huge acceleration because of what Peter just said. I think that probably you need the time. And that's why sometimes the best ideas that change the world are not happening because you put many people think about that, but it's because people work relaxed. They go to a place, they talk to each other, they have a coffee, and they comment. And that's the way that the scientists work. And I think it's important to support science and to keep on supporting science.
The open science, not that you say this is what I would like to build. No, it's a much broader picture.
Yeah, since more and more people, I guess, would come to the field as the field is growing and expanding, what would be your advice to those young researchers who are just embarking on this quantum adventure?
I think one should really say that some of the culture in the field has changed enormously. So in these first 10 years, when we collaborated on many of these things and these ideas one came up with, it was really a very small community, more like a kind of a sect, in some niche or so that many didn't really believe in. And somehow, this notion that this whole quantum computing will not work, experimentally, and why would you do it, and so on. This was for quite a long time. And then there was this phase transition somehow that from one day, we said, no, it's not going to work. Everybody believed, oh, it will work, okay? And all of these startup companies are now coming and so on. And I think that many young people are attracted, on the one hand, by really the most brilliant minds. But there's also a certain proportion of people that are attractive because they see now opportunities in the financial sense. So they don't work on these things like we did, that we were enthusiastic, maybe naive or so, but there is really something to be discovered. They're more driven by other opportunities. And it needs these people. That's very important. So the climate has somehow changed. And to keep maybe also a little bit part of this original spirit, that to be completely open and new discoveries and so on, that this is, I think, very important. So we are broadening, but things have changed. The culture has changed in the field. Yeah.
And hopefully AI can absorb some of the mercenaries, but it's always like whatever has the strongest gravity, where's the fastest climb rate. I think now maybe it was quantum computing for a bit, now it's AI. So that's good probably for the field to lighten the load of people that just want to do something quickly.
But I wanted to maybe mention something. So I believe in quantum computation. So maybe it's not that it will happen in a year or 2 years, but in the long run, there will be quantum computation, and not only quantum computation, these are quantum technologies. So every time that we're able to cross a frontier, a border, then we have new technologies that are impossible to know in advance. So it's very clear that now we cross the frontier of quantum, now we have control, we can manipulate quantum systems. And I think that it's very important for young people to know that that's really something happening at the moment. There is something that will probably have a huge impact in the next 10, 20 years, and they can live that. It's really a privilege to be able to be in a place where something is happening. That's why it's so attractive. But I think there is a reason behind that. The fact that there's a time to develop new technologies based on quantum that is still to be discovered. So apart from building quantum computers and what do you say, this thing that you want to have a close benefit, there are many open questions that will come up. So it's a very good time to enter this field for the young scientists. Of course, that's very crowded. But anyway, that's a unique opportunity that is, not everybody has the chance of participating in a revolution like this one.
I would really say that there was a time period where a new tool, quantum computing, was somehow developed and this will mature. But now is the time for a new generation that makes use of this tool to do something that we didn't think about before. And this is, I would say, basically the era that we're in right now. These are the big challenges. And this is where the young generation has to come in and provide answers.
Okay, I have two more kind of left field questions if you have time. So one is, so Roger Penrose, hopefully I'm correct about this, he has this theory which I think nobody really has any way to support yet, but that the brain is quantum, the microtubules in the brain are like 10 nanometers in diameter and maybe can hold quantum state. Can you opine on this? Do you ever think about these kinds of things, like whether the human brain has some form of quantum computing, or have you heard about this theory?
Yes, we have heard about that, of course, and it's very speculative. And if you think a little bit about that, just a little bit, then you see that it's very difficult. That something like that it's reality, because the quantum effects are very difficult to observe, or that they have consequences. The brain is at finite temperature, at normal room temperature, and so on. However, Penrose is a very clever person who has made many visionary statements. And so it's maybe it's something that he's seeing that we don't see yet and may happen in the future. So I would say that at the moment, I don't see how this can work. And there are many people don't see how this can work, but it may happen that there is something behind that that's more important that we don't see at the moment.
And the biggest difficulty is that it's at room temperature and it's all each component is bathed in water and being knocked around.
It's difficult to think how quantum effects could be observed and could have consequences at that level. And if they would have consequences, it would be very interesting by itself, because it would tell us that we can use, let's say, quantum physics in some environment that we don't know that it works. And so that's, you see, that's at this at this temperature with so many degrees of freedom and so on, that typically are away from that when we want to observe quantum phenomena. If they appear in the, say, normal life, then it would be extremely interesting. Apart from the consequences that he's proposing, which is more related to perception and consciousness and things like that, which is a different story, which is interesting on its own.
The attractive thing about it, although I also can't imagine how it would work, is that biology doesn't require understanding. So it can evolve to use whatever physics is available without understanding it. So even if the physics is nearly almost ununderstandable or unintelligible, it can still be used just by trial and error. Okay, unless you guys have any other questions, I have one final stupid question. Okay. All right, so working on quantum physics most of your life, does it cause any discomfort or like religious feelings or anything like that? Just how confusing and strange it is, or maybe it's not confusing to you, but just how different it is from normal experience. How do you sleep at night? You know, is it like a religious thing? Is it just we take it how it is, or like how do you feel comfortable with the kind of counterintuitive or bizarre behavior of all these systems? That's nothing like your daily experience.
For me, it has nothing to do with religion, but it's uncomfortable in the way that it changes the way that we look at nature. So it's not that things exist and are defined whenever we don't observe. And this, of course, has very strong consequences that I'm not able to understand. And I hope that at some point we will be able to understand. So what is the consequence of the laws of quantum physics? So they are very discomfortable, some of them. But we have to live with them because this is what it is. It's what nature dictates. But they're really discomfortable. What is discomfortable is that according to quantum physics, yes, to put it in the words of Einstein, the moon is not there when we don't look at it. It's not exactly at that position. It has not defined its position. It's not that we don't know. It's that it can be in a superposition and therefore has not defined. So the fact that things may exist that have no properties that are defined, it's really discomfortable, and that's what physics tells you. And it's a weird thing that we have to live with that, but it's not really 100% comfortable.
I would say it's actually quite amazing the fact that we learn these rules of quantum mechanics in our classes, and we teach them also, and there's a certain set of axioms that seems completely strange to some extent. But I would say that all of us have the same experience, that you learn these things and you learn them like the rules of some game maybe. But then you find out that by working in physics and working with nature and observing natures and coming up with ideas and they are realized in nature, that these rules somehow apply. And this is an amazing experience that we might have some deep questions about the foundations and interpretation of quantum mechanics. We can nonetheless play this game where we can design something in nature based on these rules, and it seems to be really true. Like building a quantum computer, even though on some level all of us feeling a little bit uncomfortable about interpretation of quantum mechanics and so on. But it seems to work. Okay, so from a practical point of view, it comes to quantum computing, we get a practical answer. It doesn't mean that we really understand whatever understanding here means.
Yeah, Mike, when it comes to that, you can just think, shut up and calculate. Just do it.
But like John Bell was saying, shut up and calculate from Monday to Saturday, but Sunday, just think.